Our presenters today, I'm going to begin with Dr. Oleg Andrich. Do I say that right?
Andrich.
Andrich. All right. Full-time faculty of the Electrical Power Technology Program at Palm Beach State College. Oleg has achieved a PhD candidate status in electrical engineering at Florida Atlantic University. He obtained his master's and bachelor's degrees in electrical engineering from Florida Atlantic University, although the majority of his undergraduate work was done at the University of Sarajevo, Bosnia, Herzegovina. Okay. Did I get it? Okay. Oleg spent 14 years at Motorola, where he was a member of Motorola Labs research teams working on various research projects on all aspects of technology development, from conceptualization through design to development and customer trials. His experiences in wireless sensor networks, self-organizing, self-healing, low-power, low-rate wireless networks, cognitive radio, speech recognition, speech coding, and signal detection. Oleg was part of the team that led the development of the IEEE 802.15.4 and Zigbee standards, which are also used in smart grid power technologies. He holds multiple patents and publications. He translated a book of fiction from Bosnian to English, the second book by Muharrem Bazdulj, nominated for the best translation into English by the American Association of Teachers of Slavic and East European Languages, 2006. Thank you, Oleg. Tony Hartzheim has more than 30 years experience in gas turbine design, testing, and analysis, as well as power generation systems design, development, and manufacture. After spending 17 years at Pratt & Whitney involved with military helicopter and fighter propulsion gas turbine design and development, he spent 9 years as engineering manager and VP of engineering at Elliott Energy Systems, Calnetics Power Solutions. He directed the engineering efforts to provide a microturbine-powered CHP system and a small organic Rankine cycle system for the power generation market. These two product lines were purchased and are currently produced by Capstone Microturbines and GE Water and Energy. In 2009, he left Calnetics Power Solutions and subsequently founded and was president of Greenheart Engineering for a couple of years, supporting customers in renewable energy, biofuel development, and distributed power generation. In 2011, he joined Agilus Engineering to support large turbine energy companies worldwide with engineering services. Mr. Hartzheim earned his Bachelor of Science in Mechanical Engineering from the University of Illinois and an International Business Specialization MBA with honors from the University of Miami. He also holds numerous patents on turbine control design. Dr. Amir Abtahi, try to get that right, sir. Associate Professor, Department of Ocean and Mechanical Engineering, Florida Atlantic University, has been teaching at FAU for 31 years and is the director of the Solar and Fuel Cell Laboratory. He established the Fuel Cell Laboratory at FAU with a grant from the United States Department of Energy in 1995. Subsequent funding from National Science Foundation and the private sector sustained the laboratory until it was combined with the Solar Energy Laboratory in 2008. Amir started his work with thermal solar panels in the early 1970s when he worked with Dr. Shaw Buckley and his patented solar diode at MIT. After completing his PhD and 2 years as a postdoctoral associate at MIT's Energy Laboratory, Amir moved down to FAU in Boca Raton, Florida, where he's been teaching and conducting research. In the early 1980s, when photovoltaic solar panels became commercially available, Amir started designing off-grid PV systems for the Caribbean and South America. He installed the first solar electric systems in Venezuela's Gran Sabana and Pajay on the border of Venezuela and Brazil. Between 1992 and 1995, Amir installed, tested numerous solar water pumps as part of a grant from the Florida Energy Office. More recently, Amir has been testing small solar village systems in Bangladesh and India. We'll be going to Myanmar to work on a village electrification project and solar water pumping system in March. And that makes me think of you as one of my heroes. Thank you. Okay, guys, go.
Okay, I think since I put a couple of slides together, I'll get the pleasure of leading this off. But one of the benefits of having a panel discussion is you can be flexible. So I'm going to lead us down a path and see where it goes. But I think one of the things also we want to do is to let you interact as we go through the discussion, obviously, and interject and ask comments as we go. One of the directions, the primary direction I think I wanted to lead this to make my point, and sorry for the subliminal advertising of the company on the charts, but the primary direction that I think I wanted to go with the panel discussion is down the road of the biofuels. We've already had discussions this morning on some of them, but one of the things that is very obvious when you get into the biofuels, there's some of them that are very consistent with the jet fuels and the turbine type fuels that are needed for operation and consistent operation of turbines in the field. The typical name biofuels, biodiesel is primarily the one that is consistent with the jet fuel, the Jet A, JP4, JP8 that are used in commercial jet and many turbines of many types, including military propulsion jets. The biofuels, biodiesel specifically, can either be created from hydrolyzed carbon-based feedstocks, which comes from everything from your McDonald's fryer drain-off to plants like jatropha, soybeans, palms, and then algae, of course, that was discussed already. The other advancing capability for developing biodiesels is microbes and the actual generation from bacteria and so forth and creating those biofuels. So these type of fuels, I think, are, and excuse me guys if I overrun to get down to the discussion item that I want to go to, but the use in turbines, from biodiesel standpoint, it's very similar to, like I said, the jet fuels in density as well as heating value, the energy per gallon of fuel. So it's not a big change for a turbine to run on a biodiesel as compared to the standard jet fuels that are oil-based fuels. The support logistics are obviously similar to the jet fuels. The one little difference is that biodiesel is more of a solvent, so you have to change some of the soft fittings in the fuel system typically. It's not a big deal though. And also the military is creating a bigger demand for those biofuels. So it's becoming a larger demand, mainly from military demand for use in the system. There are two big issues, and the second one is kind of the direction I wanted to take some of the discussion, but we can branch from other areas. One of the issues that you run into with a biodiesel is some of those biodiesels get to be a higher viscosity fluid than the jet fuels. Especially when you're cold, it creates a much higher demand and pump work demand in the fuel system to pump that fuel into the system, which can be a terrible issue if your fuel pump is not capable of powering that type of pumping viscosity of the fuel. There are also some other issues that you can run into with the fuels. Now the second issue is kind of the path I was wanting to discuss further, and this is considering not only the use of biodiesel, the primary outcome product of the process, but the byproducts of the process. One of the significant byproducts of this biodiesel generation is glycerin, which is 10 to 15% byproduct of the process, typically is used in cosmetics currently. Unfortunately, what most people end up doing is paying to get rid of the glycerin, because by the time they get paid for it, their cost of transport and generation to get to transport overcomes the value that they're getting in revenues. It is a burnable fuel. I have run turbines on the fuel. It takes some development of the combustion system to be able to run that. So it's a half the energy per gallon of biodiesel, and it does create some situations with use of it that you have to be prepared for. But I've been trying for years to get investment monies to help generate that. And I don't know that there's enough interest in some of the byproducts and the peripheral capabilities of the generation of biodiesel in the market. Okay, guys, panel discussion time.
All right, so we've had discussions from our program for a couple of years now with Tony and Agilis about different adaptations of turbines for different advanced fuels. And for us, really, both topics, biofuels and turbines, represent opportunity because in our alternative energy certificate, we have biofuels course where we have a laboratory to convert used oil into biodiesel. We've also just developed another biofuels course, biomass and biofuels, that will have the laboratory component to convert the biomass into ethanol through the fermentation. On the turbine side, we also work as part of our AS degree in electrical power technology and instrumentation control. We go through the whole process from instrumentation, installing, using all of the instruments, collecting the data, data acquisition, monitoring, and of course, finally is control. So we really have a very multidisciplinary approach, and especially because we're using the different technologies, using OSI, PI software for the monitoring, using all kinds of different instrumentation techniques, not just applicable to purely the power generation, but to analysis and the service industry of the turbines. So in addition to standard what you would expect in instrumentation control, thermocouples and pressure sensors, and we're also working with strain gauges and measuring the strain and the material fatigue on the turbines and all of the other vibration and timing issues. So we really, for us, this is a great opportunity for students to really have a global view of all of the possibilities that exist.
Well, on my part, I'm really, when I saw your background and I saw that you had been working with Capstone, was interesting because I'm pretty much consider myself a purist in the sense that I always wanted to have just only solar. As I've gotten older and run into problems around the world, I've realized that I have to compromise. And one good example of that is just about a year ago, less than a year ago, we were working on a project in Jamaica where electricity is 45 cents a kilowatt hour. And I had gone there with the idea that I was going to propose all photovoltaic system for this particular development. Halfway through the analysis, it became clear that with the power conditions and everything in Jamaica, we needed something else. And that something else were 2 Capstone turbines. And basically, it's come to a point where we all have, come from, I remember one of the gentlemen here said he was a hippie, and we have to kind of shed those clothes and start thinking complete solutions. And I mean, my background is heat transfer and combustion and everything, but I've stayed away from that. But now it's all coming together. We don't have good batteries or cheap enough or batteries that we can use yet for photovoltaic storage. So the solution becomes hybrid solutions. Biofuels, biomass, I mean, the solutions right now we're working on Jamaica are either using biogas for microturbines or biomass with organic Rankine cycle. And no matter how you look at solar systems, for this foreseeable future, if we want to be off-grid, or if we don't have a dependable grid, such as in the islands, we need another source. And that other source involves some kind of biofuel. And the other, just one more point that is really interesting. I was talking to someone, they're working on in Hawaii on a project which is solar thermal. And the problem they run into when they do the analysis is that on solar thermal, if you're running steam turbines and gas turbines, and especially steam turbines, you need continuity. You can't turn on and turn off these turbines as you get sun, etc. It takes a the equipment takes a hell of a beating. And for continuity, you need to have other sources of fuel to come on and keep the temperatures and everything steady. So biofuels, I see, have become part of the solar solution, whether I like it or not.
Yeah, and I think one of the things that you see in typical renewable energy power installations is a combination of solar and wind and turbine power on renewable fuels of some sort, where you can run the turbine as it's designed to be run continuously for a base load, and then the supplemental pieces of solar power and wind power, when they're available, are supplementing or stored for further use at nighttime or other times of the day. But one of the benefits, obviously, of going with a biodiesel or a biofuel of that type in the islands specifically, where they have to run and generate power with typical turbines running on diesel of some sort or a fuel of some sort. Biodiesels, you can handle them like water, literally. You can dump them in the ocean and it's not treated as a spill because it's a natural oil that is not a contaminant that can injure and harm the life in the ocean or the air. So there's a lot of benefits to using a broader solution in a lot of the installation sites, and use of biofuels and biodiesels is a safer choice than a lot of other options that are available.
Back to you.
Well, like I said, I think from everything that I've done with customers around the world, the best and most efficient solutions come from a combination of solutions together. Well, the design that we put together was a lot different than that. It was a more robust system than that. But as long as you operate them under the scheme that you are required to maintain the health and the robustness of the system, you're okay. There's certain circumstances you can get into issues with it, obviously, as you're well aware. But for the most part, and again, I go back to the same thing, that a turbine is designed to never shut down. It wants to run forever, literally, as long as you can keep the combustor from burning up. It'll run and run and run, and that's what it likes to do. So shutting it down and restarting it you run into a lot of different issues because of the difference in thermals. You're cooling a very incredibly hot system down to ambient temperatures and then instantly trying to bring it back up to very high temperatures throughout. So there's a lot of mechanical fights in the design of the system that you have to compromise on to survive that environment, but to make it as efficient as you can for continuous operation at a single point. If you use the systems as they're designed to be used, they're very robust and they have very long life. If you have, you treat it like a refrigerator where you can go open the door and slam the door and leave it open for a few hours and abuse it, and it just keeps going for years. I mean, that's what the market typically wants for products, right? Is to be able to abuse it and use it as they want without consideration for the actual use required in the design for the life it's intended to get, and it'll be okay. But it's like anything else. You use it like you design it to, and it'll be just fine. But that's typical of what you see in most circumstances where you sell a bunch of products that are innovative technologies, if you will. People try and find ways to integrate them and use them in different ways than they're naturally intended to initially when they go on the market. We saw this all over the world when we first introduced the microturbines, that we'd find out somebody was trying to use it in a way that just wasn't thought about before it went to the field. And you find out after it failed that, well, what'd you guys do with it? Well, we did this or that. Well, we didn't intend for you to do that, and you didn't tell us you were going to do that. So you run into a lot of situations like that where people are trying to be innovative in how they use a device that's a little bit of innovative technology and capability, and they get carried away and not working with the designers of the product to understand if it can survive that situation or not. Sure. Sure, and one of the other designs that the company that I work for, we put together an organic Rankine cycle, which is a bottoming cycle, which basically means that you take the energy off the high energy turbine exhaust and convert that into usable energy and electricity as well, because it's a organic Rankine cycle uses an organic fluid. It's kind of like a reverse air conditioner. It generates electricity by using that organic fluid in the cycle and using a condenser and evaporator system. But there's all kinds of things that you can do with the exhaust stream out of a turbine. The combined cycle for large power generation sites are the obvious example, but we've installed microturbines on buildings in Manhattan and downtown on the offsets that are their primary hot water system. They run the hot water systems. They run the chillers with the hot energy as well when they need chilling. So as long as you have a fluid with high temperatures, you can use it to generate energy of some level, whether it be for the hot system, the cold chilling, or for electrical generation as well. So, there's people get into the situation where they don't look at the capabilities of what they can do. It's more of what the best bottom line is, and they don't take advantage of the alternative means that they have for making their systems more robust and efficient sometimes, just because they just want this system and they got a mindset, this is what they need, and that's it.
Yeah, I think you bring a really good point, not just with the gas turbines and so forth and so on, but when we send out these things that people are not really used to, such as solar, let's say, rechargers. I remember we sent a bunch of solar cell phone chargers to Haiti, and they kept calling and saying the batteries are dead. And then we found out that somebody was plugging in the vacuum cleaner every night because the plug looked like the plug that the vacuum cleaner has. So in a way, as engineers, I find that to be our fault. We have to be more innovative and make sure that the plugs are different. But we run into this problem all the time. If the system is not designed in a robust manner, as you just mentioned, whether it be the gas turbine or the ORC, and by the way, the organic Rankine cycles, I think, have a good future in part of the developing world that I'm working with. Bangladesh, there's a lot of green waste. India, any of those countries, the organic Rankine cycle runs the same as a steam turbine, but at a lower temperature. So you can either use parabolic trough solar, or you can use low temperature. And I think there is potential there. But then if the system is not designed properly, and if you cool and heat, and you put these components through thermal cycling and fatiguing, you're gonna have problems. And this is what we run into. When we go away from conventional power as we're used to, and we run these innovative solutions, we forget that the power system that we're working with right now is 150 years old. So we've solved a lot of the problems. We're not going to solve these problems with these innovative systems in 5 to 10 years. And this is what I think I run into most of the time. Yes.
the only one that I know. I read the white paper on it, and some of the firms, they were having with the UFC, Unified Fuel Control, because of the balance of the hydraulics within it, to be able to censor, that it's set for JP5 for that viscosity. I'm a former level 7 mechanic, so I understood all of it. And with the bio, it's going to be a thicker viscosity, especially with your wing cells and your outskirts. So what are they doing to gently heat it without going to combustion pre-turbine?
Yeah, and typically the biodiesels are very similar to the JP fuels from Jet A, JP4, JP5, and JP8. So the viscosity difference is typically not a big deal. You get down in the cloud point and the cooler temperature effects, there's some differences in the fuels. So that's typical of in especially commercial lines and military on wing situations. You get some very cold environments on the ground as well as obviously in the air. So there's considerations for how you handle the fuel and how you maintain the robust characteristics of the fuel for pumping through your hydraulics and into the system for burning. And that, you know, we were in India running palm-based biodiesel, and it was usually hot, but it got cool a couple of times in the area, and we burned up fuel pumps because it was just too thick of a fuel to pump for the pump. So that's a situation that should be easily overcome. I mean, some gearing systems depend upon the viscosity of the liquid that they're using internal, and sometimes pumping viscosities is dependent upon the safe and continued operation of the pump and the system itself by design. So some of the designs might have to be adjusted, but typically, you know, the operational temperature viscosities are not that much different. Now, if you go into other biofuels like ethanol, then you get into a whole world of difference. But typically the biodiesels are and that's the thing too, the base stock drives a lot of the outcome properties of the biodiesel. Soybean and jatropha are not near as heavy and viscous as the palm-based biodiesels either. So, you know, it's even very dependent upon the base stock that you're using for creating the biodiesel. So, you know, that also plays into it. Capstone has currently a product line that I think has a 30 to 65, a 200, and then a 5-pack of the 200s for a megawatt. The system that we designed was a 100 kilowatt system, so it was kind of in between. They bought that line from us, so it's in that order of magnitude. The ORC system, obviously there's companies around the world that do up to 10, 15 megawatt size systems. The system that we worked with was 125 kilowatts, so it was a smaller size, and it was kind of designed for the Jenbacher output, so it was a natural fit for GE to buy it, obviously. That wasn't all unintended either, obviously. Not necessarily, because as we said, you can heat the fuel before it goes into the pumping system as you draw it, or you can heat the tanks. It's a similar situation with jet fuels because they have a similar tendency. It's just at what point in temperature the situation occurs. You get what they call clouding of the fuel, which is it starts to basically look cloudy, you know, as it gets real cold, and it gets to the point where it's a jelly substance almost when you get real cold. So you can imagine how easy that is to pump instead of like a gasoline fuel supply. It just gets very hard for a pump to pump it. But it's a problem that everybody has that uses diesel right now or jet fuel, because all those type of fuels, they have a cloud point and a low temperature issue with being able to use it and pump it. Well, yes, that's true. And when you're operating the system and it's running, it's not as big a deal because the heat from the system is kind of warming everything up. But when you're starting from a dead cold environment is usually where you have the real issues. You know, just like starting a over-the-road truck at a truck stop. That's why they don't shut them down, right? So it's the same situation when you have a land-based power system. I mean, we put the microturbines in the middle of Siberia, you know, it's a little bit cold there, and it was tough to start with other fuels and gaseous fuels, let alone a liquid fuel that's going to have issues with cold weather.
I actually have a question for you, if I may. With your, extensive background in various, with diesels and microturbines and so forth, if you had to build a hybrid system with, let's say, photovoltaic, solar, and any one of the other options, which one would you choose?
Mix.
That's not an answer.
I was talking earlier. There's a system that I think I mentioned to Oleg and Jay too. That is a simulation system that helps you balance the combination of multitude of different sources. You can model a bunch of different sizes and number of units even, and model the most efficient installation for the demand curves that you have for the site. So it's dependent upon a site, whether it's a commercial retail establishment, whether it's a 24-hour, 7-day-a-week, 365-day-a-week industrial site. You know, it could be a bunch of different situations that drive the demand, and obviously then where the site is at plays a big part as well, right? So it's hard to say, but you know, there's a lot of situations where the heat energy from a turbine exhaust is a big benefit, you know, and there's obvious situations where you want to take advantage of that, where you have processes that have to have a lot of heat energy in an industrial site. You can take advantage of that heat energy, whether you use it to generate electrical energy or use it directly for the process that's required in the industry and the process that you're involved with at the site. So, you know, I've seen a multitude of variations on the theme based, and it's driven by what you're selling, right? So.
Yeah, I don't know how much time we have.
You've got 2 minutes.
Okay. Along those lines, you know, we tried what we call a tri-hybrid, or, you know, diesel, microturbine, and solar, the chicken hatchery operation. And you're right. I mean, the only problem is initial investment. You know, when you go to someone who's doing something like that, they really hate to invest photovoltaic and then 2 other things. You want to, you don't want to make the system that complex. So, I mean, we opted in that particular instance to go with biogas and a Capstone, 30 kilowatt Capstone to keep the fans going at night. Most of the other loads came on mostly during the day, and at night I mean, one of the things that I always remember, one of my professors said, the cheapest form of energy is energy conservation. So to basically try to keep the demand down when you don't have it, I guess. But it's the initial investment.
Very good. Well, thank you very much.